Hello, this is my presentation on continued fraction expansions in rational polynomial functions. The continued fraction algorithm, CFA from now on, is an algorithm that allows to simplify rational numbers or to approximate irrational ones. With help of the CFA, one could construct a continued fraction expansion, CFE from now on, which is merely an expression of the results obtained with the CFA. In the bottom left corner, we have one of the applications of the CFA and the CFE, that is, a tower of fractions which enables us to either approximate rational numbers or irrational ones. Rational polynomial functions are arguably one of the most difficult types of functions we have to learn at school. These types of functions, however, have different applications in fields such as physics and computer science. Therefore, having an analogous CFA for these types of functions would greatly enable us to simplify the work needed to deal with them. We're going to first start off with a geometric approach to the CFA for rational polynomial functions. Although it is clear that rational polynomial functions are not linear, the function y is equal to f of alpha times x is a linear function, and we can try to obtain a CFA for that. Using the geometric reasoning for the CFA, we can obtain that the value of a sub 0 is equal to the absolute of the floor function of the absolute value of f of alpha, and that the first approximation point is equal to 1, the floor function of the absolute value of f of alpha. We can continue doing this process iteratively to obtain the formula a sub n is equal to the floor function of 1 divided by a sub n minus 1 star minus a sub n minus 1, where a sub n minus 1 star is a sub n minus 1 without the floor function. Now we're going to move on to the analytic approach to CFA for rational polynomial functions. We're going to make use of the formula used for the analytic approach with numbers, which is alpha sub n is equal to a sub n plus 1 over alpha sub n plus 1. But instead of dealing with numbers, we're going to deal with functions through long division. To understand this process, we're going to assume a rational polynomial function f of x, with which we can use long division to obtain a simplified form of f of x. We can repeat the same process iteratively to obtain that the function f of x can be rewritten as 1 plus 1 over minus 1 over 7x minus 59 over 49 plus 1 over 49 times minus 7x plus 23 divided by 144. Now we're going to see some approximations with an arbitrary f of x. The red curve is going to represent the original function, the blue curve is going to represent the approximation, and the black curve represents the error term. This first is an approximation with the analytical approach with one term. This second visualization is the analytical approach with two terms. And this is the analytical approach with three terms. We're now moving on to the geometric approach. This is the geometric approach with one term. This is the geometric approach with two terms. And finally, this is the geometric approach with three terms. To conclude, both methods, the analytical and the geometric, serve to effectively simplify the function through an analogous CFA for rational polynomial functions. The analytical approach tells us more on the overall behavior of the function, whereas the geometric approach tells us more on the specific behavior of the function at a point. That was my presentation. Thank you for your attention.